So statistics is just a part of a research methodology, and it's not everything. And some people get confused about whether they want to do a course in research methods or in statistics. And this course in the epidemiology and biostatistics, we're very much focused on research methodology as regards epidemiological studies, and then also looking at some statistics. Biostatistics just meaning that it's statistics relevant to human data. If you're planning on going on to a higher degree by research, or if you're studying in a master's program, then you might want to know where statistics fits into the broader scheme of things. And there's different types of research depending on what we're trying to achieve. So I think most people have heard that there is quantitative research where we want to measure stuff, and there's qualitative research where we're usually trying to describe things. And these have different philosophical backgrounds, and if you're interested, you can look up into what is ontology, what is there to know, epistemology, how can we know it, methodology, how can we acquire this knowledge. Then for any particular study, you will have the specific methods that you're using, and this will be different depending on whether it's quantitative or qualitative research. And then finally we get to the analysis, and we're kind of skipping all of this stuff and we've looked at the methods, and now we're looking at the analysis. But if you move on to do other research, and in some of the papers you'll see that they also have some qualitative aspects which I don't cover, and these might be things that are drawn from interviews or focus groups or other kinds of observations, and you'd do a different type of analysis for that type of data. When we get to looking specifically at statistics, broadly speaking, there's two types of statistics. We have what's called descriptive statistics, and as the name gives away, we're simply trying to describe stuff with numbers and pictures. So it's about collecting, organising, summarising and presenting data. The other branch is the inferential statistics, and the inferential means we want to make an inference, and this is related to hypothesis testing. And we're interested in looking at or determining relationships and perhaps making predictions depending on the context. And you'll see in papers that they always start the results with some descriptive statistics, because for any research we need to know who participated in it. And so we start the results section with descriptive statistics, and then it will move on to the inferential statistics where they've actually used a test. I don't know why I keep looking off to that corner, because I'm actually not in real life. That's a bit odd. My second monitor is actually over to the right. Inference. So you can Google the meaning for that if you're not familiar with the word. A conclusion reached on the basis of evidence and reasoning, or the process of inferring something. Circular definitions are not helpful, I find. So the scientific method: ask a question, research existing sources, formulate a hypothesis, design and conduct a study, draw conclusions, report results, and that will usually lead to asking another question. And this is what we're trying to do in this course. We're starting with the question, does something work, or is there a relationship, or is there an effect? How do we collect the data to look at that? And then how do we test that data to see what evidence we have? There are lots of different statistical tests and procedures available, and the right test will depend on what type of data you have and the question that you're trying to answer. We are covering quite a few tests in this course, and this is a flowchart that I have drawn up specifically for our course, and these are the things that we will be looking at. And all the way over there, my arm doesn't reach that far. These are the ones that we'll be looking at in this course. I'll just get out of the way of that. So you might like to print this out to have it as a reference, or you could draw up your own flowchart if this doesn't make sense to you. You can also Google statistical flowchart, because there's loads on the web, and you might find one that you like better. So this is one that I found on the internet. This is more like a decision tree. So you start, you answer the question yes or no, and then bloop, 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 you end up. And you'll see that all these tests here, pretty much all of them are the same. There's a couple we're not doing, we're not doing some of this advanced stuff. But for the most part, you'll see similar tests to what I have on my flowchart. And here's one more example, which is color-coded. We're not doing any survival analysis. So again, you're welcome to use any off the internet, and you could just go through and match up the names to what I have on mine, and then you'll know if you're looking at the right type of tests. So when do we want to test something? Well, obviously we want to test the outcome. Is there a difference between our groups at the end? But we also want to test stuff about our design. So when you were designing your protocols, I would have said to you in class, and perhaps if you came to see me individually, is there any other data that you should be collecting, any other variables you should be collecting in case it confounds the results? So we usually collect things like age and gender. You might also collect a variable related to education or socioeconomic status, or other health attributes. You might also collect data about smoking or eating meat or something else that might be related to your study that could potentially affect the results. So you'll often find in any particular paper there seems to be an awful lot of testing, and the way you know if a test has been done is because a p-value has been reported. So every time you see a p-value, it means another test was done. And we're usually testing a couple of things. We give our descriptive statistics about who participated in a study, and in that spot we often want to test, are our groups approximately the same at the start? We want to know that we've started from a good foundation. And then we'll get to our inferential statistics, where we're really interested in testing the hypothesis driving our research. Is this intervention effective? So we want to know, is there a difference in the groups at the end? So here's a little example paper. The objective is to assess how age-related social comparisons, which are likely to arise inadvertently or deliberately during assessments, may affect older people's performance on tests that are used to assess their needs and capability. So it's a very long way of saying, I guess, if you make old people feel old, do they actually perform worse? So what they did was they randomly assigned participants into two groups, where either they would be sort of compared with younger people to make them feel old and worthless, or they would not have that comparison with younger people, and then they wanted to assess their hand grip strength and persistence. So it's a really interesting study. I found there are some problems with the design, and I encourage you to read it and think about how could they have done it better, or what are the main problems with it. But it's a really interesting topic, and it can illustrate a lot of the things that we're talking about. So the main outcome measures they have are the hand grip strength measured using this device here. I should Google that actually, see what it looks like. I'll do that after. You can do it for yourself now if you like. So in the design stage, are our groups similar? I'm right in the middle here. This will do. So in the table 1, and you'll find that this is common across nearly every paper you read, that table 1, which is the first table in the results, will pretty much always have participant characteristics or demographic characteristics. And if we have a look at these, actually maybe I'll just walk a little bit out of the way. Oh, I'm off the side. So if we have a look at the age in the comparison group, and by comparison that means they were getting this age-related comparison, which presumably made them feel old. The mean age was 83, and the control group, the mean age was 82. The gender, 18 female in both groups, and 9 male and 10 male in the other. So we can see that the age and the gender is fairly similar. Education looks fairly similar, school leaving age. So this is an older cohort, and so 50 or more years ago it would have been quite common to leave school earlier. So leaving school at 15 would not be unusual. Pretty sure my grandma left school before she was 15. I'll have to ask her. Might have even been 13 or 14. Type of residence. Oh, I'll have to scroll down. I can't remember what the codes mean. Own home or other residence. And this may make a difference, because if you're in your own home and you have to do more stuff for yourself, then you're likely to be a little bit more independent and perhaps have a stronger group strength. Whereas If you're in a residential facility or if you have a lot of stuff done for you, then it may mean that you just become weaker due to not doing certain things. And then we have self-reported arthritis, which might be different from a doctor's diagnosis of arthritis. So self-reported arthritis, because that may affect your grip, strength and persistence as well. So if we were looking at this, what would we want to see? We would want to know that our intervention group or our comparison group, in this case, was similar to the control group, because then if we see any difference at the end, it will likely be due to the intervention and not because we started off with some differences in the groups at the start. They've done some testing here, and we haven't covered these tests yet, so we're not going to look at this column, but this is the test statistic, which is commonly reported, and it gives an indication of which test was done, F-test, chi-squared test. F is usually analysis of variance, which we'll do next week. And then the p-value, what's the probability of observing the data if the null hypothesis is true? And we'll come back to interpreting p-values. So you can see that each time we've got a p-value, they've done another test. So they've actually done 5 statistical tests in this table, just to show who the groups were. And they haven't actually got to the outcome yet. So you'll notice that there is no mention of grip strength or persistence in this table. So the first table is not about the outcomes, it's about the participants. Now, I can't remember what was in table 2, but here I've put up table 3, and this is where we've got the main outcomes for the study. And in this case, they've done a more advanced analysis where they adjust for other variables, and we will see this later in the course, how we can do this type of statistical adjusting. And here you'll see they've also put in the mean values with the standard errors, that's the SE, for comparison group and control group, and then they've put some details on of the statistical testing. So we've had 2 tables of interest, one about the participant characteristics and then one about the main outcome. And in each case you can see they run quite a few tests. And I've just about walked off the end of my other screen, which is why I keep sort of cutting off over there. So understanding how statistics are reported. The statistical plan, or what you intend to do with your data, is a part of the methods, and the actual testing is a part of the results. Any one research question could contain several smaller specific hypotheses, and it will likely involve more than one test. So you will usually see several tests done in any one paper. So this is an example of the statistical plan. And you can see here, so up the top they've said what software are they going to use for their analysis, what value are they going to take as being significant. 0.05 is obviously very common. They've talked about a bit about their data, and then they say they're going to use ANOVA and chi-squared analyses, and then they say they're going to do some correlation and some other stuff. So all of this stuff here would go towards the end of the methods section. And you probably won't understand all of it just yet, but I'm pointing it out now so that as we learn more and more tests, you can perhaps revisit some of these examples and think, oh, now I understand why that was there and what it is that they were putting in there. The reason it's important to have a look for the statistical plans in the methods is that often the results don't actually include how the testing was done, and you often have to try and work it out. In this case, they have said, I need my pointer back, they have said here in the results that they compared using ANOVA. Oh, my pointer's not quite reaching that far. But that doesn't always happen in the results. Sometimes you'll get a sentence that's more like this one here, where they just have some p-values, perhaps some means, perhaps some confidence intervals, perhaps an OR, which if we can remember back to week 3 or so would be an odds ratio. And it's not always immediately obvious what they've done to get these numbers, and we often have to work out what they've done based on the values that they report about what we know about the study and what they put in the statistical plans. And here we've got another results section And this is very typical to be reporting a few values with a lot of abbreviations. CI for confidence interval, OR for odds ratio, M for mean, and then P for p-value. So hopefully you'll get comfortable picking out all those numbers. I personally really like papers where they put a chart in. I think it makes it much easier to understand the results, especially the key result. And they really should include confidence intervals wherever possible. Just putting in the hand grip strength between the two groups in itself doesn't tell us a lot. We need to know how confident we are of those estimates. And here we can see that it looks like there might be a bit of a difference. So if we have a look at the people who did not have a social comparison made, they weren't made to feel old, and the ones that did, oh, yep, my point is not reaching that far. So it does look like there's a difference, but this line here is the confidence interval. And where would be, if it's a 95% confidence interval, then we're 95% confident that we've covered the true value, meaning the true value could be anywhere along here, and actually it could even be outside the confidence interval. And there's quite an overlap here between the confidence interval for one group and one for the other. So it's possible that this difference is not statistically significant. We can't always show the significance easily on a graph because this picture in itself will only contain two variables, and they might have done a more complicated model where they adjusted for other variables. So just because something looks not significant on the graph, it's still possible that it was based on what analysis they did. So although graphs are really helpful, we need to have them in conjunction with a table and a little paragraph explaining what they found. So the process of hypothesis testing. Now this is something that I expect you've done before, but we're just going to go over the process and then we will work through examples doing each one. Let me move out the way. Oh, I've moved right off the screen. I'm here. Right, so this is a little snippet out of the corner of the flowchart, which is why it's a little bit blurry, but I've written out the process here. So we start off by needing to know what is the variable type of our main outcome. This is what really drives the choice of what is an appropriate test. We need to know our main outcome, how is it measured, and what kind of variable is it. So I mean, is it continuous? Is it categorical? If it's categorical, is it nominal or ordinal? If it's continuous, or is it a scale variable? Is it a count variable that we want to treat as continuous, or is it a count variable that we'd be better off putting into categories? So there's a little bit of leeway in the middle there about how we treat some of those ordinal variables and count variables depending on what they look like. And this is where we need a little bit of practice in doing statistics to understand some of the nuances in the data analysis. If your data is definitely in categories, it's quite easy, and if your data is definitely continuous, then it's quite easy. It's just the middle ground can get a little bit grey sometimes. So we need to know our main outcome. We need to know what our main comparison is, which is our explanatory variables. We can use a flowchart to work out what's a suitable starting point, what's a suitable test to start with. Does the data meet the assumptions of the chosen test? So any test will make certain assumptions about the data, and we have to see if those are true. If they're not true, can you use a different test, or is your data so bad that you just can't test it at all? Once we've chosen a test, what is the null hypothesis? And this is usually that there is no difference, no association, or no effect. Then we let the computer do all the hard work and the crunching to find out what is the evidence against the null hypothesis, and this is the p-value, and then we'll use this to draw a conclusion. So you can see here that I've got for my my chart, if our outcome is nominal, then we would just simply come down this column. If our outcome is continuous or scale, we would come down this column. If it's in the middle, then it's possible we could treat it as any one of these three types of data, and this is where it can get a little bit confusing. So in Sci 110, you would have done a chi-squared test which came out of this column, and you would have done a t-test which came out of this column, and you would have missed all this middle ground. And this is what we're kind of focusing on in this course, but we're still looking at the test that you did in Sci 110 as well, or PUB 708 if you're in the master's course. So the outcome for when we're choosing the appropriate test is the outcome or the dependent variable for the particular test in question, not necessarily the main outcome for the research project. So if we were testing that the groups are equal at the start of the study, the outcome in question might just be the age or the gender. The hand grip strength might not come into it until later. So we've got to look for a particular test, what is the dependent variable or the response or the outcome that we're testing between the groups. Then we need to know, what are we looking for with this outcome? So have we got paired data, like before and after data? Have we got 2 separate groups that we want to compare? Have we got 3, 4, 5 groups that we want to compare? And that will change what type of tests we do. So paired is the same as might be matched or before and after, 2 independent groups, more than 2 independent groups. If we're comparing with another continuous variable, then we're looking for a relationship, and we might also be doing a more complicated analysis controlling for other variables. So essentially testing several variables at once, and then we come down here. But we're going to start off at this top part today. So we would probably start off by looking at what we call the parametric test, and we would choose one of these, and then we would have a look at the assumptions. Now, broadly speaking, the assumptions are that, so hard to keep my pointer in the right spot. So broadly speaking, the assumptions are that the data is approximately normal, there's no large outliers, and we have equal variances. And you'll see these written out quite nicely in the Laird statistics page with a few others, just checking that you've got the right sort of data, and we check each of these quite systematically. If the assumptions are okay, then we can go ahead and use the test. If they're not okay, then we would do the crossover into the next column and have a look at the next test over. So you've probably seen this word around, parametric and non-parametric. If you don't have a math background, you might not be familiar with what parametric means, but a parameter is something that we can use to describe a distribution if it meets, if it conforms to a shape that we're expecting. So if we have a normal distribution, we can actually, because we know the shape of it, this bell shape, we can describe a normal distribution by just giving the mean and the standard deviation. So these 2 numbers, the mean and the standard deviation, can completely describe data which conforms to a normal distribution. And those 2 numbers are called the parameters of the normal distribution. So when we see something called a parametric test, it's usually assuming that the data is normal. It doesn't actually have to be. We can have parameters for other distributions, but this is the common one. If we see a parametric test, it's usually assuming that the data is normal and the parameters that we're interested in are the mean and the standard deviation. If it's non-parametric, it means there are no parameters which describe the distribution because it's not normal or it's not conforming to a shape which we can describe easily. So that's what a parameter is, and that's why we get this naming convention of parametric tests and non-parametric tests. So if we can't use a parametric test, can we use a non-parametric test as well? And typically the non-parametric tests don't have a lot of assumptions. So if we were going to do a paired t-test, but there was something very wrong with our data and it wasn't appropriate to use a normal approximation or assume that it came from a normal distribution, then we might use the Wilcox and signed ranks test instead. And this is why the flowcharts are handy, because normal people don't remember all these names, obviously. If we were going to use an independent t-test, but we found that there was a problem with the data, then we might shift over to using the Mann-Whitney U instead, because it wouldn't have so many assumptions. These parametric tests where we assume that they're normal, it's always about testing the mean, because the mean is how we describe the center of a normal distribution. But in a lot of cases, the medians are better measures of the center of a distribution. We actually want to compare the medians instead. So if we know from the outset that we want to compare median values, we might move straight to one of the nonparametrics tests. And there's quite a lot of them. You'll see a lot of names. There is actually a Moods median test. The Mann-Whitney U will get used, and you'll see some others floating around. The layout in SPSS is actually quite easy for the nonparametric test. You don't have to know any of these names. You just have to know that you're doing a nonparametric test. So once we've chosen our test, then we need to know what the null hypothesis is. So if we're testing the means, that would be there is no difference in the means. If we're testing medians, it would be there's no difference in the medians. If we're testing proportions, it would be that there's no difference in the proportions. And the alternative is always that there is a difference. What is the evidence against the null hypothesis? So if we have a little look at this picture here, you can think about how convincing each of these situations would be. So if we wanted to know, does Santa have a bias towards one colour of present than another, and we collected this data, most people would say this is not too convincing. And why would they say it's not convincing? Because the sample size is small. We have 4 red, 3 green and 5 yellow. And they would say, well, there might be a difference here, but I don't think you've got enough evidence to prove it. And if you can remember back to when we did our sample size and power calculations, that's what this is about. What kind of sample size do we need in order to be convincing or to be able to detect an effect if it is there? Now, if we had this much data, would you be convinced? And this is a little bit more convincing. So we might say this is really weak evidence. This is some evidence. And then we might say, gosh, if you've tallied up this many presents, that's really strong evidence. So the strength of the evidence is what we're interested in. And we summarize this with a p-value. So you might remember this guy. Ronald Fisher was the sort of inventor of the p-value. And he was the one from the lecture on confounding, which said, taking a poor chap's cigarettes away from him would be like taking a white stick from a blind man. We can just ponder that for the moment. So he was a very smart man, but had a blind spot, if you will. So why do we use this p less than 0.05 is significant? I'll put my hand down for a second. I can actually put my other hand up, but I tend not to do that too often. So historically, 0.05 is used as a cutoff for significance, and that's just because Ronald Fisher said he thought that would be a good idea. And he was mostly interested in agricultural experiments, and he was dividing up plots of land to see what crops grew better under certain conditions and stuff like that. But it's not a hard and fast rule. If you get something less than 0.5, it doesn't mean that you've proven, and I'm doing air quotes, which you can't see. And if you get a p-value that's greater than 0.5, it doesn't mean your research was worthless. So it's just a line in the sand, and it's probably more helpful to talk about strength of evidence rather than trying to say you're going to prove or not prove or accept or reject. I really don't like that terminology at all because I think it's misleading. It's much better to talk about, I think, evidence as a lawyer might talk about it. Have you got reasonable doubt? What is the strength of the evidence? It's very difficult to absolutely prove something true, but we can talk about how strong our evidence is and how good a case we have. So common interpretations of the p-value. Put my hand down now. There we go. So usually we take this approximate value of 0.05 as being significant, and we might say that this was moderate evidence against the null hypothesis in favour of the alternative, so moderate evidence of an effect. Smaller than that, we might say we've got strong evidence, and then if the p-value is very, very small, we've got very, very strong evidence against the null hypothesis, because it means there was very little chance of seeing that data if the null hypothesis was true. And this process of hypothesis testing we will go over a lot in class, because I know that this is quite challenging for a lot of people. And if the p-value is very large, it means we've got no evidence that there's any difference. So we summarize the test. This is the last step. Usually in terms of significance, we give the p-value and some measure of the difference. So if we say, yes, we found a difference, well, what was it? Which colour did Santa prefer? Clearly he preferred the yellow ones, the yellow presents. So we would say we found very strong evidence that Santa is biased towards yellow presents, and he gave out, I don't know, what proportion more yellow presents than red or green, something like that. So in a paper, you'll see that they include some values for what they were comparing and probably the test statistic, which will come out of the test, and we'll see that later on. They'll also give the p-value. Now, I've put a few notes in here about this test statistic. I will be pointing this out for every test that we do. And if you've done tests by hand in Sci 110, we didn't do any by hand, I think, in PB 708. But if you've done some tests by hand in a previous course, you may have calculated these test statistics and then compared them with tables of values to find the p-value. We're letting the computer do all of that work for us. But the particular letter assigned to the test statistic actually does tell us which test has been done and gives an indication. So if there's a T test statistic, which usually means they've done a T test. So you don't have to be able to interpret the value of the test statistic itself. That will change for every test, but the p-values are consistent. So we want to know what the test statistic is and we report it, but we interpret the p-value. So here we can see, as shown in Table 3, the effect of condition of this social comparison for the older people on mean strength was significant, and they've given p-value is equal to 0.038. The comparison group had a mean strength of 6.9, and they've given the confidence interval, and the control group had a mean strength of 11.02. And they've given the odds ratio, saying that the performance is reduced by almost half by the presence of a comparison. And they're talking about this age-related comparison, which might make older people feel old and perhaps useless. Here's another table summarising p-values. This is quite good, but it is a bit of a joke. So you don't actually, well, hopefully you won't need counselling if you get a p-value approaching significance. With regards to your project, you're not being graded on whether or not you found a significant result. You're demonstrating your capability of carrying out the research process, including the statistical testing. So it doesn't matter whether your results are significant or not, you can still get a good mark if you understand what you're doing. That said, it is more satisfying, I think, if you get a significant result. You feel like you've achieved something, and that's part of the reason we do this power calculation at the start, because we want to know if there is an effect there, what are the chances that we're going to be able to find it with our particular study. So lastly, and this is quite a long lecture, what am I up to? Half an hour, 33 minutes, failing to reject. So if you don't find a significant result, it does not mean that there is no effect. It means that you couldn't find it. So if there is an effect, the study was perhaps not powerful enough to demonstrate it, or perhaps there was something else going on. And we have to interpret this within the context of how well the study was designed, and also what does other research in the field show. So if 20 other research studies have found that goji berries make you more beautiful, and you're the one study that shows that it doesn't, then maybe there was something wrong with your study. Maybe you just had this odd result, the 5% of studies which can't find something which is there. Maybe there was something else going on. But if there's lots of studies, if we have 20 studies in a row which all show that there's no evidence that goji berries make you more beautiful, or whatever I said a second ago, then it probably means that actually goji berries don't make you more beautiful. So this is why we need replication in science. One study in itself is not enough to show anything. It gives an indication, and then we want to replicate, and perhaps we want to adjust the design or do it in different contexts, and then we build a body of evidence around whether or not something is useful, whether there's an effect, whether there's a relationship, or if there's nothing going on. And it can take quite a while. In some ways, it can take longer to show that something is not true than to show that it is. So once this idea that vaccines caused autism caught on. It's taken a really good 10-15 years to debunk that. And the original paper which sort of made this claim in the first place was actually shown to be a fraudulent research study. It wasn't real. And even though that was fraudulent, just because the idea got out there, it's taken a huge amount of research, high quality research, to debunk that. And it was never true in the first place. So sometimes proving something not to be true is a lot more difficult than proving it is true. Okay, so we'll leave this lecture here. Sorry it's so long. And then the next videos will be about how we run specific tests. And this week we're doing the t-test and the Mann-Whitney U.